Yeah, so I'll be talking about particle flows and constrained particle flows in this talk, and feel free to ask me questions while I'm talking. That's completely okay. Okay, yeah. So the first uh, high-level picture is what exactly are particle flows. Essentially, we just have a number of samples from a prior distribution, and then we're trying to combine it with an observation. So from a Bayesian standpoint, we're trying to combine a prior with a likelihood. And so ultimately, we want samples from a posterior. So essentially, what we want to do is we want to define a stochastic differential equation to move the samples from the prior to the posterior. And yeah, so for example, you can think of the Langlois MCMC, but yeah, that's basically the idea with this from a high level. So the questions we are trying to answer are how do we define the optimal drift? So in what direction do we need to move the particles so it samples the posterior? And then how do we define the diffusion? Or how big or small should it be? And should they be, how do we model the correlations and so on? And then the third question is, do we have any information about the distributions itself that we can leverage, or can we make our own assumptions about it? And yeah, and the fourth question is, what do we do if the states live on a particular constrained manifold? How do we define the flows then? What happens there? And especially because it's stochastic, it's definitely going to violate the constraint manifold. And yeah, so while I focus on particle flows in the context of data assimilation, because this is a SciML mini symposium, the question I want to pose is, can we see neural network training as a state estimation problem on the weights? And yeah, with that in mind, I'll talk about our framework, the variational Fokker-Planck. So a quick introduction to what data assimilation is. Imagine we're trying to simulate the temperature on Earth. And so we have a high-dimensional set of states that describe the evolution of this temperature, but our models are frankly not that good. And so like at some point, we will start to diverge from what is actually happening on Earth. And so for that reason, we need to combine it with observations. And unfortunately, we cannot measure the temperature at every single discretization grid point that we have. It's expensive, infeasible. And so we need to somehow combine sparse and noisy observations with the states that we have. And that's, in a sense, the data assimilation problem. So at each step, we evolve the previous best estimate, and then we combine it with observations to get a new best estimate, and we repeat that cycle forever. Yeah. So with that in mind, there's like a slight nuance about how we combine the observations. So there's filtering and smoothing. So in the filtering, we just combine the states with the observations only from that particular point in time. But for the smoothing flavor of things, we sort of combine it with a trajectory of observations from multiple time points, and that requires us to also model the evolution uncertainty on the states. And this is a pretty well-known problem, and there's a lot of solutions that are already there, such as the ensemble Kalman filters and particle filters and the variational methods and so on that are used operationally. So, but our goal is to construct a very generic framework for particle flows, we just call it the variational Fokker-Planck, and our framework allows us to make a large number of assumptions on how we want to move the particles and everything, and as we'll see in the upcoming slides. And what we are also claiming is that different assumptions in this framework give rise to different or well-known particle flow filters that are already in the literature. So that's our claim. Let's see. So for the theoretical aspects, a lot of our work was inspired by the flow filters by Van Leeuwen and Sebastian Reich. And for the more, I guess, computational ideas, it was inspired by the last two papers by Krauss, Lewis, and Fred Dahm. But all of them are pretty great papers, and I think at this point this may also be a little outdated. But yeah, so those were the ones that inspired us. So how do we do this? We have a number of samples from the prior distribution, and so we are trying to define a stochastic differential equation, so with the drift term and the diffusion to drive it towards the posterior. And what I'm not showing you there is that it's a McKean-Vlasovian process in nature. So in a sense, the drift and the diffusion are dependent on the distribution of the samples itself. But for notational simplicity, I'm just not writing it out explicitly. And so defining that Ito process, it essentially entails that the distribution also evolves in time, and that's given by the Fokker-Planck equation. So what we derive in the paper is how do we get a drift that minimizes the KL divergence between the prior distribution and the posterior, and I call it a p tau because it's the prior distribution in transit towards the posterior, so it's in a sense instantaneous while it's moving to the posterior. And in our framework, we asymptotically evolve it to infinite time to get the analysis, but essentially we sort of terminate it when the particles start hovering about and the distribution does not change. So in our work, we also prove that this converges in the sense of the distributions in the KL divergence. And yeah, that's basically what the figure over there is showing. We have some particular, is that the light? No. Yeah. So let's see. So the essentially after crunching through on a bit of variational calculus, we end up with the drift that looks like equation 2.2. So each term that it has is it's pretty intuitive to explain it. So the first term, the log gradient of the posterior, essentially it pushes the particles towards the posterior, and then the log gradient of the distribution of the particles in transit, it kind of has a regularizing effect. So say if we did not have any diffusion in the process and the distributions matched, your drift would end up being 0. So that's the intuitive explanation there. And then we have this positive definite matrix that we can sort of use to precondition the flow dynamic. And yeah, the key thing here is that p tau is a parametric distribution that we can estimate from the ensemble or particles that we have, and that's the main idea there. And the diffusion tensors in the drift, they essentially account for having a stochastic term in the full process. And so what kind of assumptions can we make here? It's extremely broad. So far, the posterior distribution, it's actually a combination of the prior and the observation. And if we assume that both of them are Gaussian, we can recover the 3D var or 4D var gradients in the filtering or smoothing cases. But we do not have to assume that anything is Gaussian, and there can be any generic distribution you choose. As long as you can evaluate its log gradient, you're good. And it's the same story with p tau. And then for the A matrix that we have to precondition the flow, we can sort of choose the identity operator because it's simple. We can also choose to scale it by the probability of the particle there, and that results in a Stein-like gradient. And then if we choose it to be equal to the diffusion tensor D, it gives us Langevin dynamics. And so like we can recover a large number of well-known flow filters in that way. And then for the diffusion itself, we just typically model the covariance. So if it's a gigantic PDE system, we just use like a scaled Gaussian or Mattern covariance. If it's a smaller ODE system where the correlations are not that are not as simple, we can use like a climatological covariance with some scaling and so on. So the next step to this is how do we evolve this flow in the in pseudo time, and the easiest choice is to use the Euler-Maruyama. So equation 2.3 is the discretization that you have there, pretty standard stuff. But the problem is a lot of the time the drift term, it makes the time stepping extremely stiff. So can we do anything about it? Well, so we tried using the backward Euler Maruyama, but it turned out to be extremely expensive, and its convergence is also complicated. And so a happy medium is to use the Rosenbrock Euler Maruyama, so which is basically what we have in equation 2.4. So that's equivalent to like a single step of the of backward Euler plus the stochastic term. And this allows us to take reasonably large time steps to get to the posterior. Okay, so the next question is, what do we do when our states are constrained to live on a certain manifold? So over here we just have an equality constraint, so g of x equals 0. So what we have is that the probability of samples being outside that manifold is 0, and we do not want any samples from there. But standard filtering and smoothing schemes, they cannot account for this, and typically it just violates these physical constraints. So for example, like we work with the a number of fluid simulations, and we want to conserve like the mass, energy, entropy, and so on. And using standard data assimilation techniques, you cannot preserve these constraints, which are pretty important. And so the big question is, how do we obtain analyses that are consistent with the constrained manifold? And to just drive this point further, we just look at the simple pendulum. So in Cartesian coordinates, so we have 3 constraints on it. The first one's the length constraint, so we do not want to change the length when we assimilate. And then the second one's the tangential velocity constraint, and the third is the total energy constraint. We do not want to violate any of these when we assimilate stuff. And so we're just considering a situation where we have a forecast given by the 5 blue pendulums, and we have the true pendulum in red, and then we have an observation in yellow. So we are observing the x and y coordinates of the true pendulum, and the observation error is sort of exaggerated for this figure, but yeah, so if we use a standard data assimilation technique here, we just use the ensemble-Kalman filter, we end up with a bunch of samples that are completely off the constraint manifold. And so what we would want to do is have samples that lie on the constraint manifold. And some important work here is listed. I think the one we focus on is the post-processing by projection. So essentially, the idea is once you do the assimilation, you just project it back. And I mean, a lot of the times it works, but the major issue with that is if your samples are too far away from the constraint manifold, you maybe you just cannot project it back. And one of our experiments will show exactly that. And so for this, we modify our Ito process by a little bit. We turn it into an index to stochastic differential algebraic equation. A lot of big words, but it's easy enough to solve. We're essentially just projecting the particles along the Jacobian of the constraints. So you can think of it as having a Lagrangian multiplier in optimization, and we're essentially solving for the algebraic variable or the Lagrangian multiplier using root finding. And so when we discretize it, we are essentially taking a first step along the drift and the diffusion, and then after that we are projecting it back onto the manifold. So the advantage of this is that we don't stray too far away from the manifold, and so projecting back, it happens all the time. And yeah, if the I guess the explicit drift is again unstable, we can use the Rosenbrock order discretization on it. And so we have a number of experiments here. So in the first one, we just look at the ensemble spread. Essentially, what the figures are showing is that as we increase the diffusion, our ensemble spread increases, which is pretty obvious. So yeah, so the idea is we can use these sort of diagnostics to tune for the optimal diffusion scaling. And in this figure, what we do not show is that for an ideal rank histogram, we want it to be a uniform distribution, but somewhere between the diffusion scalings of 0.05 and 0.1, we have the optimal scaling. And then we throw our methodology on the Lorentz 96 problem. So this does not have any constraints, and I guess in the interest of time, all I'm going to say is we basically do pretty well compared to the standard methods that we are comparing against. So our methods are LVFP, GG, and LVFPS, which is the smoothing version. With Gaussian assumptions, we do very similar to the localized ensemble Kalman filter and the Kalman smoother. So that's pretty good. And the next experiment that we have is we look at the Navier-Stokes, and the well, I don't have all the settings written out, but it basically mimics a Fourier circulation in an oceanic basin, and we have like a gigantic number of states and a gigantic number of constraints. The number of constraints is so high because we have the divergence constraint at each discrete point. And we have an extremely small ensemble size of 10 particles. So there's that. And all the assimilation settings, so the choice of the time step is essentially around 6 hours in this non-dimensional time and so on, trying to imitate a real problem. And what we see is that with respect to the RMSE, or the spatiotemporal error over time, we perform comparably with the standard methods. But with respect to the constraint itself, we see that in certain situations, the so LETKF with projection, or it fails to obtain the correct entropy on the manifold, and so sometimes it's just impossible to project things back. And I guess that's the conclusion of the talk. So basically, we have a generic particle flow framework, and we have extended it to incorporate equality constraints. So, and we can extend it to have other types of constraints as well, such as inequality and box constraints using ideas from optimization. So have like a penalty function maybe, or a barrier function, and so on. So I guess for future work, so I know me and Arash have talked about it at many points. So we want to try using this framework to train a Bayesian neural network. So so it allows for easy uncertainty quantifications because we have an ensemble, and the added advantage is that we can also have gradient-free training using the ensemble approximation of the gradient. And so it all seems good, but the question is, will it converge quickly compared to the standard methods? And we want to explore it at some point. And that's it. Yeah, so all this was done with my collaborators, Adrian, Sandu, Andre Popov, and Reed, and those two are the papers that we have. Thank you.
We have a very few